Ever get that feeling where you just want to like understand something really complex, but you don't want to, go through all the like reading all the articles and stuff. So
Yeah.
that's what we're all about here. And today we're going to look at something pretty cool from computer science, undecidable problems.
Yeah.
And you can think of this as like a shortcut
Exactly.
to understanding
Yeah.
something that might sound intimidating,
hmm
but it's got some really mind-blowing implications for what computers, can and can't do.
Yeah, absolutely. And we've been looking at a transcript from a Code Curious YouTube video. It features Mrs. Julia Alano,
Okay.
and she is from Hamilton Southeastern High School.
hmm
So, we're getting a nice, kind of educational angle
Right. Yeah.
on this really interesting topic.
Yeah, and the mission for this deep dive is pretty simple.
Yeah.
We want to explain what undecidable problems are, and maybe even more importantly, what makes them so unique.
Yeah.
And like a fundamental concept to computer science.
Yeah, totally.
So, to kick things off, what makes a problem decidable in the first place?
So at its core, a decidable problem is one where you can always get like a yes or a no answer. Doesn't matter what input you give it.
Yeah.
So there's like a reliable step-by-step process. We call that an algorithm,
Okay.
and it's guaranteed to give you that correct answer every time. So if you think about an algorithm like it's a recipe,
Right.
you follow the instructions, you get the same result,
Okay. Yeah.
always.
Yeah, that makes total sense.
Yeah.
And the video gives this great example of figuring out if a number is divisible by 3.
Yes.
Can you walk us through how that works as like a decidable problem?
Yeah, totally. So the algorithm for checking divisibility by 3 is pretty simple.
Yeah.
You take any number,
Okay.
and then you use this thing called the modulo operator.
Okay.
That's the percent sign. And that gives you the remainder after you do division. So you take your number, you divide it by 3, you see what the remainder is.
Right.
If the remainder is 0,
Mm-hmm.
that means the number divides perfectly by 3.
Okay.
So then the algorithm will say yes or true.
Okay.
If it's any other remainder, like 1 or 2,
Mm-hmm.
the algorithm will say no or false.
Okay.
And the cool thing here is that this method will always give you the right answer.
It's guaranteed.
Yeah, it's a guaranteed process.
Okay. So, decidable
Yeah.
means a clear yes or no
Mhm.
every time, thanks to a reliable algorithm
Exactly.
or a recipe. So, let's flip it on its head.
Right.
What is an undecidable problem?
Okay, so an undecidable problem is where that guarantee of
Yeah.
a yes or no answer for every single input that you give it
Yeah.
doesn't exist.
Oh.
So the video transcript makes this really good point. While it might be possible to find what we call algorithmic solutions for like some specific instances or examples of an undecidable problem,
yeah.
there is no one algorithm that can solve all versions
Yeah.
of that problem.
That's a really important point. It's not that we can never answer it. It's just that there's not one thing that will answer it every time.
Yeah.
And the example that they always use for this is called the halting problem. What is
Yeah.
the halting problem asking us to do?
So the halting problem asks, if you have any computer program
Okay.
and you give it a specific input,
Mm-hmm.
can you determine beforehand whether that program will eventually stop running
Uh-huh.
and give you like an output,
Right.
or will it just keep running forever in what
Yeah.
we call like an infinite loop?
Oh, we've all seen that, right?
Yes,
It's
exactly.
like you open up a website and it
Yeah.
just sits there, and
Yeah.
that little loading bar is just got it.
Yeah.
And you're like, is this ever gonna finish, or is it just broken?
Exactly.
That's the halting problem.
That's it.
What makes that so hard to solve universally?
Well, the really interesting thing here is just the inherent challenge
Yeah.
in trying to predict
Right.
the future behavior of a program.
Right.
Like, if you
Yeah.
think about it, to know for sure that a program will never stop,
Uh-huh.
you would essentially have to watch it run for an infinite amount of time.
Well, we don't have that kind of time.
No, we don't.
We've got other things to do.
Yeah, okay, exactly.
But the video also talks about like programs that take just an unreasonable amount of time to finish.
Yeah.
So how does that like blur the line
Yeah.
between halting and just running forever?
Yeah, this is a really crucial point. So imagine a program
Yeah.
that runs for a really long time, like days, weeks, even years.
Okay.
Is it like just doing this super complex calculation?
Yeah.
And it's like slowly but surely making its way towards an answer?
Okay.
Or did it actually enter an infinite loop
Right.
and it's going to go forever?
Yeah.
Without having like complete insight into what that program is doing,
Right.
it becomes impossible to definitely say, yes, it will eventually halt.
Right.
Or, no, it's going to run forever. So this ambiguity
Yeah.
is a big reason why the halting problem is undecidable.
So, like, if I go to a website and it takes forever to load,
Yeah,
my computer isn't actually solving the halting problem.
exactly.
Is it? It's not figuring out if the website would have eventually loaded.
It's not, no. So the video actually illustrates this really well.
Okay.
So when a website or like an application seems to hang or freeze,
Uh-huh.
your computer isn't like running this sophisticated analysis
Right.
to determine if it's in an infinite loop.
Okay.
What it does is it sets a timeout.
Right.
So after a certain amount of time,
Yeah.
the system will just give up.
It's like, all right,
Like website's not responding.
I waited long enough.
Yeah. And this is necessary
Right.
for us in the real world,
Yeah.
but it's not actually a solution to the halting problem.
So it hasn't figured out if the program would have eventually finished?
No.
Just decided?
It's just like, I'm done waiting.
Yeah, I'm out. Yeah.
Okay. That makes sense from a practical standpoint.
Uh-huh.
So let's clear up some misconceptions about this whole thing.
Yeah.
So the video brings up this statement. An algorithm can be used to solve an undecidable problem. True or false?
That is absolutely false.
Okay.
So, as we've been talking about, the very definition of an undecidable problem is that there is no algorithm that can solve it for all inputs.
So if there was one, it wouldn't be undecidable.
It would be decidable, exactly.
Okay, cool. Here's another one. If a programmer encounters an undecidable problem, they can just use an algorithm that works most of the time. True or false?
That's also false.
Okay.
So, while in some scenarios, a programmer might use what we call heuristics
Okay.
or approximation techniques that work pretty well,
Yeah.
those are not true solutions
Right.
to the problem.
Okay.
They're workarounds. So, an algorithm for a decidable problem has to be correct every time.
Okay.
No exceptions.
Right.
For undecidable problems,
Yeah.
such an algorithm doesn't exist.
Okay.
So what do programmers do?
Right.
They have to come up with alternative strategies. Okay.
So one thing they could do is restrict the problem to make it more manageable.
Okay.
They could also use methods that don't guarantee an answer every time.
All right. So let's do a recap of the big ideas here.
Okay, sounds good.
Like, what are the big takeaways?
Right, so the big takeaway here is that undecidable problems are like a real thing in computer science.
They exist.
Yeah, they're not just problems that are like hard to solve.
Right.
They're problems that we can prove, like no algorithm will ever be created to solve them.
And the big difference between a decidable problem
Mhm.
is that a decidable problem does have that step-by-step algorithm
Exactly.
that'll always lead to a correct yes or no answer.
Yeah.
Just like our
Our divisibility by 3 example.
Right, exactly. Like, is
Yeah.
this number
Yeah.
divisible by 3?
Yeah.
So if there's no algorithm that can handle every possible situation,
Mm-hmm.
then it's undecidable.
By definition, that's exactly right.
Okay, cool. So the halting problem is a great example of that.
Yes, definitely.
So we've taken this pretty thorough look at this stuff, and we've seen that
Yeah.
some problems aren't just hard for computers.
Yeah.
They're impossible for computers to solve every time.
Yeah.
And it's not just a matter of needing a better algorithm.
Mhm,
It's like the problem itself
Yeah.
is the problem.
Exactly. That's a great way to put it.
So this kind of leads to a bigger question, and I want you to think about this.
Right?
Given these like limitations to computers,
Yeah.
these problems that we've proven are undecidable,
Mm-hmm.
how does this change the way we think about
Yeah.
the future of technology?
That's a really good question.
So like if you think about things like AI
Right.
and just like our basic understanding of what computers can and can't do,
Right.
what does it mean to know
Yeah.
that there are just some things that they can't do?
I think it makes us reconsider like what we can even expect from technology.
Right.
Like maybe it's not always about finding the perfect algorithm.
Yeah.
Maybe it's about understanding these limits
Okay.
and working within them.
Okay, cool. Well, thanks for taking this deep dive with us. Hopefully you understand undecidable problems a little bit better
A
now.
little bit better.
And yeah, think about that question that we
Oh,
talked about.
yeah.
And we'll see you next time for another one of these.
All right. Sounds good.